Now that we have a Laplace transform of the Dirac delta, we can actually use it in examples. So remember, our first example that inspired us to invent the Dirac delta was this example. So we had a 1 kilogram mass hanging from a 1 Newton per meter spring, and after 10 seconds, we delivered 1 kilogram meter per second of impulse. So let's add some initial conditions. If this mass starts motionless at its equilibrium position, then let's find its position as a function of time. So before we actually solve this using a differential equation, let's just use our intuition to guess what ought to happen. So if we graph the position of the mass as a function of time, since it's starting motionless at its equilibrium position, that's 0, so it's going to start at 0, and then at time 10, we're hitting it with a hammer. And if we deliver 1 unit of impulse, that means it's going to start moving upwards. But if it's moving upwards right after this hammer blow, there's no more forcing. And if you have this system, a mass on a spring with no damping, and it starts moving upwards, then it's just going to oscillate in some sort of sinusoidal. So we expect some sinusoidal to show up. So up until time 10, it's just 0, and then at time 10, it changes to a sinusoidal. So that's kind of what we expect to have happen. So with that in mind, let's actually do the computation and see if this is the kind of thing that we get. Okay, so for a 1 kilogram mass and a 1 Newton meter per second spring, we're going to get 1 times y double prime plus 1 times y equals our forcing function. And we have 1 unit of impulse at time 10. So it's 1 times Dirac delta at time 10, so t minus 10. Okay. So, simplifying everything, this is y double prime plus y equals Dirac delta t minus 10. And now we can take the Laplace transform of everything in sight and do our usual thing for solving a differential equation. So we get Laplace transform of y double prime, that's s squared times Laplace transform of y minus s times y of 0 minus y prime of 0 plus Laplace transform of y, which is just Laplace transform of y, equals Laplace transform of t minus 10. And this is e to the minus 10s. All right. Now our initial conditions make these terms both go to 0. So factoring out the Laplace transform of y on the left-hand side, we get s squared plus 1 times Laplace transform of y equals e to the minus 10s. And now we can finish solving for Laplace transform of y. Laplace transform of y equals e to the minus 10s over s squared plus 1. And now we need to find an inverse transform. So hitting both sides with the inverse Laplace transform, we get y equals inverse transform of e to the minus 10s over s squared plus 1. Okay, now we can calculate this inverse transform because we have a shift in s, multiplication by an exponential in s, and we know that multiplication by an exponential in the s world turns into a shift in t in the t world. So t is going to be shifted by 10 and multiplied by a step function. So u of t minus 10. And the inverse Laplace transform of 1 over s squared plus 1 is sine of t. And don't forget to replace t with t minus 10 times step function at 10. And then finally we can do our shift. So sine of t minus 10 times u of t minus 10. So what does the graph of this look like? Well, first of all, it does look like a sine. So if it weren't shifted, this sine would look like this. But it's being shifted by 10. So over here at t equals 10, that's where this first starting at 0 and then increasing, that gets shifted over to 10. Also, because the step function is 0 to the left of 10, our graph of this solution y is 0 until we reach 10, and then it follows this sine curve. But that's exactly what we expected, right? This is matching up with our intuition perfectly. If we have a mass hanging motionless on a spring and then we hit it at time 10, it sits there until time 10, and then once we hit it, the spring takes over and gives us an oscillation. So this worked perfectly. It gave us exactly what we expected. Let's look at another example. So let's find the behavior of a 1 kilogram mass suspended from a 6 Newton per meter spring and also attached to a 5 Newton per meter per second damping mechanism if it starts motionless from its equilibrium position, and we bump it twice. So we give it 2 impulses, one at time 1 with 1 unit of impulse, and another bump at time 4 with 2 kilogram meters per second of impulse. So since we have a 1 kilogram mass, our y double prime term will have a 1 in front of it. I won't write it, but it's there. Our damping mechanism is 5 newtons per meter per second, so 5 times y prime, plus, and then our spring constant is 6 newtons per meter, so 6 times y equals, and now we write our forcing function on the right-hand side, and our forcing function is just these 2 bumps, these 2 impulses. So we have an impulse of strength 1 at time 1, so delta of t minus 1, and it's times 1 in front here, but I won't write that because it's implicit, plus, and then there's another bump, another impulse at time 4, and it has strength 2, so 2 kilogram per meter per second. I'm sorry, this should be Newton meter per second, shouldn't it? Sorry. No, kilogram meters per second. Right. I was right the first time. Okay. Great. Now that we have this Laplace transform written down, or now that we have this differential equation written down, we can just hit the whole thing with Laplace transform. We get, so coming from y double prime, we get s squared Laplace transform of y minus s times y of 0 minus y prime of 0. Okay, and now for our y prime term, plus 5 times Laplace transform of y prime is s times Laplace transform of y minus y of 0. Okay, and now Laplace transform of 6y, so that's plus 6 Laplace transform of y equals, then on the right-hand side, Laplace transform of these Dirac deltas. So Laplace transform of the first one is e to the minus s plus 6 times Laplace transform of delta of t minus 4, that's e to the minus 4s. Okay. Of course, all the initial condition terms are 0 because this thing is starting motionless from its equilibrium position, so 0, 0, 0. All the terms left on the left-hand side have a Laplace transform of y in them, so we can factor that out. We get s squared plus 5s plus 6 times Laplace transform of y. Then on the right-hand side, e to the minus s plus 6 times e to the minus 4s. Okay, and then on the right hand, or divide both sides by our denominator here. So actually, I'm going to do it this way. E to the minus s plus 6e to the minus 4s times 1 over s squared plus 5s plus 6. And I'm going to do it this way because this denominator factors, so we're going to have to do partial fractions here. So this is s plus 3 times s plus 2 in the denominator. So we get Laplace transform of y is e to the minus s plus 6e to the minus 4s times, so we're going to do partial fractions here. One term has s plus 3 in the denominator, the other term has s plus 2 in the denominator. And so cover-up method, if we plug in s is minus 2 to get the coefficient here, we get a 1. And if we plug in minus 3 to get the coefficient over there, we get minus 1. So let's see, if we put these back, over a common denominator, it looks like I got the signs wrong. So we're going to need a minus here and a plus here. So if we put these over a common denominator, you get a minus s, a plus 3, and a minus 2. Yes, okay, there we go. So we're about to take inverse Laplace transform. So let's write it like this. Now each exponential, when we do an inverse transform, each exponential is going to give us a different shift in time. So it makes sense to separate the two exponential terms. So I'm going to take all this stuff in brackets and distribute it to the two exponential terms separately. So we get e to the minus s times minus 1 over s plus 3 plus 1 over s plus 2 minus, so plus, sorry, 6 times e to the minus 4s times the same stuff, minus 1 over s plus 3 plus 3 plus 1 over s plus 2. Okay, now we can take an inverse transform. So I'm going to skip a step in the inverse transform and immediately write down these exponentials in s as a shift in time. So this first piece, we're going to have a shift in time. Time is going to be shifted by 1 and times u of t minus 1. Okay, and then now inverse transform of the stuff in brackets, there's a minus e to the minus 3t plus e to the minus 2t. Okay, so that's just this first term. And now let's do the second term. So plus 6 times, right, we're going to take an inverse transform, but we know at the end we're going to have a time shift by 4, and we have to multiply by a step function shifted by 4. And this inverse transform is going to be the same because it's the same stuff in brackets. So minus e to the minus 3t plus e to the minus 2t. Okay, and so finally our solution is minus e to the minus 3 times t minus 4 plus e to the minus 2 times t minus 4, all times, I'm sorry, this should be 1, not 4, all times u of t minus 1 plus 6 times minus e to the minus 3 times t minus 4, that's the one that's minus 4, plus e times minus 2 times t minus 4 times u of t minus 4. Okay, so This is our solution for what happens on this mass on a spring. So because the damping was so strong, it's no surprise that it's overdamped and we just get exponentials. But to see if this matches up with what our intuition would be, let's look at a graph. So I'm going to make a cut and type in this big awful formula, and we'll look at the graph. Okay, I have this big awful formula typed in so that we can look at a graph. As I was doing that, I noticed that this 6 wasn't right. You probably noticed before me. This 6 should actually be a 2. So that was the strength of our second impulse into the system, and it was 2 units of impulse, not 6. I think I copied down a 6 from the left-hand side accidentally. But let's look at a graph. So, of course, what we're expecting to see is that nothing happens until time 1, and then somehow we get exponentials up until time 4, and then we get different exponentials. But let's have a look at this. So here is GeoGebra, and let me turn on the graph here. Okay, so nothing happens up until time 1. At time 1, essentially what is happening is that the velocity of the system gets set to be 1. That's what it means to give it a 1 unit of impulse. Since it's not moving at all, and the mass of the system is 1 kilogram, 1 kilogram meter per second of impulse will change its velocity by 1 meter per second. And so the slope of the tangent line right here is actually 1, but then of course immediately the damping takes over and the spring starts pulling on the thing. And so its velocity decreases, and since it's overdamped, we get some sort of exponential. And then there's another impulse that's twice as big at time 4, so the slope of the tangent line on this initial part after the impulse is 2. And of course, once the impulse is over at time 4, then the spring and the damping take over and we get exponential decay again.